So I've been listening to the talks from the morning, and I can confidently say that computing is moving towards energy efficiency solutions, especially in the AI accelerated domains. I was reading a news yesterday that it says a year usage of ChatGPT model consumes power equivalent to powering up the entire New Zealand country for 3 months. So energy efficiency is very important. And if we speak in that direction, as Vivek pointed out in his 2020 paper on roadmap to exascale, data movement or data accesses are one of the key challenges in escalating costs of energy. We can categorize the architectures into two spectrums, two categories based on the data accesses. On the one side, you have coupled access execute paradigm. On the other side, you have decoupled access execute paradigm. In the coupled access execute paradigm, so it's the microprocessor issues both the compute and memory operations together. Okay, so you have one single binary that is having both the compute and memory operations intertwined. And to help reduce the latency of the memory operations, a range of hardware techniques have been invented, such as hardware prefetching, out-of-order execution, and so on. So they are helpful in reducing the latency, but they are power hungry. On the other side, we have decoupled access execute paradigm that is gaining popularity these days, especially for AI models. In the architectures based on this paradigm, memory accesses to the caches or to the scratch pads are totally decoupled from the compute, which means it's not like one single binary that is going to be running on this. So you have specialized processors for the compute units, and you have simplified processors specific to the data movement and address generation units. So these architectures based on this paradigm offer better energy efficiency compared to the traditional coupled architectures, because the hardware becomes very simplified and lightweight. And the responsibility of decoupling the computations with the memory operations is given to the compiler now. The hardware becomes very lightweighted. And because of this, it becomes very energy efficient and performant for a class of applications. But the challenge with this is that the software complexity grows up. But I think for a class of workloads like ML, I think we can manage that complexity very well. So, and also the name EDDO architectures, it's recently put, I think in 2017, Buffet, there was a paper called Buffet, came up with the terminology of EDDO architectures. Essentially, EDDO architectures are simply nothing but these decoupled access execute paradigm architectures operating over the scratch pads, not on the caches. So IBM AIU, the picture on the left is part of a single core of an AIU. Okay, so and AIU is built on the principles of the decoupled access execute paradigm. So you have a bunch of computational units like PE, SFU, these units, and you have scratch pads like L0 scratch pad, L1 scratch pad connected to these computational units. Now you have additional units for the address generation and data movements, such as L0LU, L0SU, and these units. For example, if my compute unit PE wants some data from the scratch pad L0 at a point in time, it's the responsibility of the L0LU unit to deliver the data to PE, which means this PE never issues an instruction to load the data from L0 scratch pad. So you have programs for L0LU that is coherent and synchronized with the PE. So it's the responsibility of the software to generate program in such a way that at a time when PE wants the data, L0LU sends the data to PE with a FIFO connection. And on top of that, so you have lots of these such cores sitting around trying to do the orchestration and communication and doing the computation together. And on top of that, each unit might have their own ISA specific to an application and the kind of role it plays in those models. The most important thing in this slide is each core that you are seeing, whether it is a compute core or it's a load unit core or a store unit core, they are specialized pertaining to a domain, and they are also simplified. For example, these cores could be typically single issue, in order, maybe they might not have branch predictions to begin with, or no execution space, no execution stack, and all these things, and exposed pipeline and all these things. So the complexity is growing more and more towards the software. So let's look at what kind of challenges they pose to the software stack, these kinds of architectures. So I view the challenges in 3 dimensions. One is in the programming, and another thing is scheduling, and the third thing is in the code generation phase. In terms of programming, EDDO architectures require differently a fundamental different approach to programming. So you have heterogeneous units. Compute units can be different across the things in the hardware, and you have different load store units. So the programming of these devices fall under the category of MPMD model, which is the multiple program, multiple data style. So on one end, one can think of a sequential program intertwined with loads and stores and compute, and you can have an automatic decoupler similar to automatic parallelization, where it decouples the instructions into them and then try to run. There are so many challenges with that approach. On the other side, giving an abstraction to programmers to write these decoupled programs from the get-go itself only. But of course, there are challenges with that side as well. So it's an open problem at this point in time, what are the right abstractions to program. But right now, the existing architectures like AIU or the Samba Nova or the NVDLA architectures, so they are relying on the PyTorch and other frameworks at a very higher level, and then compilers in between try to figure out the scheduling, decoupling them, and generate the code. And when it comes to the scheduler, now how do you map the computations onto this diverse set of computational and data movement engines? So scheduling goes beyond loop transformations. So you would have to look at where my data transfers needs to be placed, how do I synchronize with the other units, and concerns of deadlock, data races, and all these things come together. And the complexity of this scheduling step sort of tangled with the programming step that we take. And on the last side that I'm going to talk in detail now is about the code generation. So these cores are very much simplified. On one side, it reduces the burden on the compiler to do code generation, but at the same time, it puts pressure on it to do better code generation than what is possible right now. And I'm going to talk about one aspect of that. For example, what are the implications of not having no execution? What are the implications of having no execution stack? So if you don't have an execution stack, you cannot have function calls. You cannot do register spilling of variables onto the stack. So which means if you are not able to fit your variables into the finite number of registers you have, then you are doomed. Your compilation failure. So you have to come up with even better register management techniques for these kinds of cores. So yes, so by design considerations in the AIU, each core is simplified with not having an execution stack to begin with. So now the compiler needs to be more smarter during this register management to fit all the variables into the finite registers you have in the cores. I'm going to take some example and an approach that we have taken to deal with this problem. So I'm going to start with a motivating example. So this is a load unit L0LU. Let's say that is the one that is trying to load the data from Scratchpad and send the data to the computational unit, like let's say PE. And as an example, let's say array A is allocated on the Scratchpad starting with address 0. Okay? And you have a triply nested loop ijk with a static loop counts. And then you have a load operation inside that. So you are viewing this array, you are accessing A with a linearized subscript, but still this is an affine subscript. You load the data and then send the data to the unit, for example, in this case, PE or U. Okay? So one way of lowering this program into an IR is I would have multiplications and additions inside the loop nest. Of course, that is expensive because I would have to do 2 additions, 2 multiplications inside the loop body for every iteration. Or I could use scalar evolution techniques to turn them into addition operations. Or what if the hardware doesn't even have scalar multiplications to begin with? So let's say if your hardware says, no, I can't do multiplications, how would you lower this down? So the snippet on the right shows a possible lowering by not considering multiplications at all to begin with. So this is a sample MLIR based IR where the loop carried variables are simply realized using loop iterator arguments. You see 3 loopness ijk corresponding to whatever you are seeing here ijk. Inside the loop body you have a load and send operation. Basically it's loading from address arg3 and then sending it to unit u. Okay. Now you see additions happening at the end of each loop nest. These are simply nothing but the multiplications are realized using loop carried additions. For example, arg3 corresponds to the k and the coefficient of k is 1, so that's why you are incrementing by 1 in every iteration. And later arg2 corresponds to the j dimension, and then in each step you are incrementing by 128. So you have an addition of 128, and similarly for I you have 256.
U a register or?
U is some unit, some computational unit.
Is it a memory buffer?
No, it's a FIFO you can think of. So basically load units are connected to compute units, and these two are connected by a FIFO. So when a load unit is sending data to a compute, it means essentially putting into that FIFO. And then the compute unit is taking from the data from the FIFO. So if I look at this particular IR, and let's try to reason about register allocation. Okay. And the traditional way of doing register allocation is by constructing the live ranges and see how do we assign these registers. And if I do the live range calculations manually, let's say for percentile 1, its live range starts from line 1 and then it gets used only in the line 2. That's it, its live range ends. If I take arg1, it starts from line number 2 and then it all the way goes back to line 12, because this is the one that is incrementing the stride by 256. So that's why you see live range from 12, and arg2 coming here, it live range starts from 3 and then goes all the way to 9 because that's its last use. So similarly R3, 4 to 6 and so on. If I look at this particular live range picture, I can see there are 4 live ranges overlapping at the same time. So I need at least 4 registers in order to map this program onto the hardware. So any Oracle register, any optimal register would at least need 4 registers. As I said, there are 4 live ranges overlapping. So now what if I say that I can map this program to a single register? So that's the thing I'm going to talk about, and that is using the polyhedral affine methodology now. So assume that I'm just ignoring iterators for now, so don't worry about allocating registers for ijk. For all the rest of the variables I'm talking about. Okay. So let's see how do we realize realizing this program with a single register. Okay. So the approach that we call it as an affine based approach for live range reduction, I'm going to explain with an example on how it works. So the very first step here is we want to compute a variable's value in terms of affine expressions of prior definitions. In the sense, in this program, if I look at arg1, for example, if I look at percentile 1, it's simply 0, constant assignment. If I look at percentile 5, it's arg2 plus 128, so it's the affine expression of that. So if I look at arg1, the initial value is percentile 1, and in every iteration I'm incrementing with 256. So in symbolic terms, arg1 is simply nothing but its initial value percentile 1 plus loop iterator value times 256. So that's percentile arg1, and percentile arg2 you can derive in the same fashion. The initial value is arg1 plus j times 128. Of course, you know arg1 is nothing but 1 percentile plus I times 256. When you substitute, you get these affine expressions. Okay. Once I calculate a variable's value in terms of the prior variable definitions, I can do something magic here, which is I would replace a variable. So I have an expression, let's say a equals to f of x. Now I can replace the value of x with a definition that is closely defined to the variable a. In that case, my live range gets reduced. So let me explain here. So these are the variable calculations that we have done on the prior slide. Now if I look at line 6, in the original program I have percentile 3 equals to percentile arg3 plus 1. But if I look back into my dictionary, arg3 plus 1 is simply nothing but percentile 2. So I can simply substitute this RHS with percentile 2, that's what we could see. And now if I come to the interesting point about line 9, percentile 5 equals to arg2 plus 128. And arg2, if I go here, arg2 can be realized in terms of percentile 4 by simply subtracting with 64. arg2 is nothing but percentile 4 minus 64. So I simply substitute that value percentile 4 minus 64 plus 128. So percentile 5 simply becomes percentile 4 plus 64. Okay, I do the simplifications like that. And now let's compute the live ranges. Now the live ranges become simply linear like this. They no longer overlap with each other. So which means I simply need one register to map to all the variables here. So now let me pause here and say something here. How is this possible? So what made this possible? There are some properties that we are exploiting to realize this. Firstly, when we are doing these calculations of variable values, we know the loop bounds being constants, because if they are constants, then only you can express percentile 4 in terms of arg3 plus 64 times this guy. So we know the loop bounds are constants, and we know the strides are constant. They come from the affine expression of load in the beginning. So because it's 128 times I plus 256 times j. So those are affine expressions. So ML workloads lend themselves to these properties. So you know the shapes ahead of time, which means your loop counts you know. The address patterns are affine, so which means your coefficients becomes constants. Now, as a result, what happens is that these expressions that you are seeing on the left, they end up becoming mostly affine. If they are not affine, we simply say, hey, we cannot resolve this guy and move forward. But of course, by doing so, we lose optimization opportunities. So now a single register is sufficient enough for all the variables excluding iterators. So I just explained an approach where simplifying the hardware by removing the power-hungry units, it poses challenges to the compiler. And in compiler, we can use program properties pertaining to a special class of workloads and do optimizations better. So with that, I think I'll conclude with all these things. But I just wanted to say a few words about Vivek. Firstly, I should say, Vivek, it's a blessing to be advised by you. I think I was a very amateur explorer before doing a PhD. I think, Vivek, you transformed me into a person who could do an independent research and giving me opportunities to grow in different aspects of my life. And I'm going to briefly talk about that. So, Vivek, as everybody said, you made seminal contributions to the field of compilers, which are still applicable to the modern architectures. So, this is the statement I always say to you, even in my PhD, that whenever I pick a problem to work on, I always found a reference back by Vivek. I was like, Vivek, you already solved this problem ahead of time. So Raj asked me to share some of the memories that I have with Vivek. Apart from technical and leadership excellence that Vivek exhibited, but there are few things that I wanted to say. This was about when I was writing my first research paper. Vivek asked, Prasanth, go ahead and write a research paper, the first one, to the impact submission. I wrote the paper, but I wasn't very good at writing the paper. It was, when I look back now, I find it funny by myself. So, but Vivek never discouraged me. So in fact, I would say he wrote most of the paper along with Joan. And then he suggested me to take a class in writing and then become better. So you never condescended me or you never disappointed me. In fact, you gave me opportunities to grow. And the second thing, everyone's PhD is not rosy. You have ups and downs. And especially during the lows, it really matters how your advisor helps you in that situation. Vivek, you have been very helpful during my low times. And also when I made mistakes, you accepted me. And then also opportunities to grow. So when I moved to Georgia Tech with Vivek in PhD, so he advised me to join the Leadership Edge course at Georgia Tech. So now if I am able to lead code generation efforts with people of 8 to 9 from different groups at IBM, I think that's majorly because of this. Thank you, Vivek, for giving me these opportunities. And you helped me on the practical advices in both professional and personal settings. So I consider you more than as an advisor in my life, Vivek. And one last thing to end with. So I was asked in the morning, like, how did I first learn about Vivek? So everybody talked about Vivek's PhD and masters in 1987 and 82. I want to talk about 1981 here. So Vivek's undergrad advisor was Professor Keshav Nori, and he was the professor who taught Vivek compilers, programming languages, and in fact this project was with Professor Keshav Nori, and apparently this project was selected as the best undergrad project during that time, and it was in the initial days of the computer science in IIT Kanpur. And it's the same professor who taught me compilers in my undergraduate. I think that's how I first learned about Vivek Sarkar and then his contributions to compilers. And in fact, one of the reasons why I also sort of motivated to do research as well. So thank you, Vivek, for everything. Thank you, Raj. Thank you.
We are into the break time. So we'll take a break. Let's try to come back in 15 minutes.